In this problem, we're concerned with two types of energy, kinetic energy and potential energy. Kinetic energy is due to the speed, that is, the length of the velocity vector, and it grows with speed in a quadratic fashion. It contains a factor of the velocity vector of the spacecraft, the length of that vector squared, meaning if we increase the velocity by a factor of 2, we're going to increase the kinetic energy by a factor of 4, which tells us that speeding is really dangerous. There is another factor in here, the mass of the spacecraft, and then there is an additional factor of 1/2. Potential energy concerns the position of the spacecraft. As we move the spacecraft away from Earth, we have to invest energy, and that's going to become potential energy. This is the distance of the spacecraft from the center of the Earth. When we fire the rockets to get it away from Earth, we invest energy, and that energy leads to a change in potential energy. In the case of gravity, it's easiest to have the potential energy be negative all of the time, and only when the spacecraft reaches infinity, its potential energy will be 0. And the formula for that is pretty much related to Newton's universal law of gravity. We've got the gravitational constant. We've got the product of the masses, mass of the Earth, mass of the spacecraft, and in this case divided by the first power of the distance. If you remember, in the force we had the second power of the distance. And of course we have to have a minus sign in front. If we double the distance, we go to half that original value, but still with a minus sign. If these are the only kinds of energy in our problem, and if energy conservation holds, we know the following. The sum of these two energies has to be a constant. It must not depend on time. It has to stay at its initial value. And that's something we can use to check our numerical solutions. When this expression does not stay at its original value, we do know that we're in trouble. Note that energy conservation does not hold in all models. In particular, if we have friction and ignore the heat produced by that friction, energy won't be conserved.